Good afternoon, everyone. Did you guys have a good weekend? Probably not like mine. I was planning a great weekend. Distinguished alumni dinner, having friends in town, but couldn't do anything because I'm not feeling well. Did any of you go to the Distinguished Alumni dinner? How was it? It's nice. Was it in in which hotel? Like close to the lake? That one? Four Seasons. Okay. Yeah, I always go to those ones. So that's one of my favorite events of the year, but I couldn't make it, unfortunately. Okay, so we have a midterm on Friday. Today we're gonna talk about the last theoretical part about Wellbore stability, and on Wednesday we're gonna have a review. I'll talk about the homework for faults, which I know that it's causing some trouble, and also for the homework of Wellbore stability Wednesday. So come prepared for that. And if you want to also take a look at the practice exams, just do that too. I uploaded 2 exams that you can work on already. Okay? Yeah, Mr. Dodd.
Is that homework due this week?
That homework, yeah, is due actually on Wednesday, I believe. I, I think I didn't upload it yet, but yes, I forgot to do that. I'm sorry about that. But it's due, yeah, it's due before the exam. It's not too complicated, okay? I'll post that today. All right, so we're going to talk about 5 other factors that affect Wellbore stability, and you should know. The first one is temperature. And temperature is going to cause strains whenever you have a variation of temperature. And this might seem already quite straightforward. It is not that straightforward. So imagine that you have a piece of rock and you lower the temperature. To move in all directions. And let's say here it's just sitting on the surface. Able to if you lower the temperature, as the rock will shrink, and that shrinkage is going to be proportional to something which is called the thermal dilation coefficient. And because this is a deformation caused by temperature, we call it a thermal strain. And that strain, the change of length divided original length, is going to be proportional to the coefficient of thermal dilation times the change of temperature. So this one over here is the coefficient of thermal dilation. What do you think are the units of this coefficient of thermal dilation? This is a strain. 1 over temperature, 1 over K, 1 over C. You can define it in as you want. All right. So that's what happens to a rock which is unconfined, which is unconstrained. But that's not what we find in the subsurface. In the subsurface, we have rocks surrounded by more rock. So let's try to think about an example that will be a little bit more realistic, in which I have a rock which now is sitting between 2 surfaces and those surfaces do not move, and let's say that now I have a very strong glue between that surface and the rock, and again I apply a change of temperature which is negative, which means I lower the temperature. What's going to happen to the rock in this second case? Will it shrink? In this direction, there is nothing preventing the rock to shrink, so probably it will shrink. But on the vertical direction, I'm saying in this case that these walls are not moving, and because they are not moving, let's make it part of a bigger solid. Because it's not moving, then instead of strains, what I'm going to develop inside the rock is a tensile stress. When that tensile stress is higher than the tensile strength of the rock is going to. So you can break the rock just by changing the temperature if you have these conditions in which you do not allow the rock to shrink. Opposite, if you were to have an increased temperature, and if you don't let the rock dilate, that's going to generate a compressive stress. Well, in the wellbore environment, we're going to have something similar to this. And it's going to be more or less like this. Let's imagine a cross section of a wellbore. Our wellbore in this condition. And now inside the wellbore, we apply a change of temperature which is negative. What do you think happened to the wall of the wellbore? Will it move towards the center or further away from the center? If you lower the temperature and the rock is shrinking, so this is the rock, and you're lowering the temperature of the rock away from the center. So if the rock is shrinking in all directions, it should move away from the center. And notice also that if we consider a wedge of rock around the wellbore, like this one, now it's going to have a radius which is, so it means a longer perimeter, and what that means is that the rock in the hoop direction is going to develop a tensile, and this tensile stress variation in hoop stress due to temperature is going to be equal to, first of all, it's going to be proportional to the change of temperature, delta T. The higher the change of temperature, the higher that change of stress. We also saw before that that's proportional to the coefficient of thermal dilation. And in addition to that, this thermal stress for these conditions is also going to be proportional to the Young modulus of the rock divided 1 minus the Poisson ratio. In order to have a stress, I need units of pressure, and this is what gives me those units. And the modulus times the strain, as we know, give us a stress. In this case, the strain is, this is the thermal strain. This is the modulus, this is the resultant stress. And this is the stress that I was telling you that before that we use in calculating the breakdown pressure. Let me get to there. If you remember, the calculation of PV included the pore pressure, the stress on isotropy, the tensile strength, but also you need to take into account the thermal stress when it is significant. And this thermal stress can be quite large. For typical conditions, you can have, when delta T is large, this can be in the order of several thousands of psi. And it's all going to depend on the modulus of the rock, the dilation coefficient of the rock, and the temperature. But probably this is the one that varies the most. And from some applications, if you are just drilling, probably the changes are not going to be that large. But these changes could go all the way from 0 to 200 degree Fahrenheit, or more or less 0 to 100 degree C. It depends on the application that you're dealing with. This is an issue many times when you drill a wellbore and then you want to run a waterline log, and some of these tools, when you need to run them, they require a lower temperature, so you need to circulate a mud at a lower temperature than the formation. And when you do that, you may trigger thermal stresses which diminish the stress around the wellbore and could cause the wellbore to break just because of change of temperature. So you have to be very careful with that. So sometimes just by logging a well and changing the temperature of the mud, you could cause an event of low circulation. So you need to be you need to calculate this number and make sure that you are within the range that the wellbore is not going to fail. And again, all of this together, sometimes it can amount to 1,000 psi or more. So it is quite important. All right. So temperature, low temperature is not good for the breakdown pressure, for tensile stresses, but sometimes it may be good for breakouts, because this is going to lower your hoop stresses. But in general, it's not going to be good. Okay. Let's go to the second one. The second one is something which is called shale instability, and it's due to the properties of the building blocks of shale. What are the building blocks of shale? What do you have in shale? Clay. And do you remember what are the properties of clays? Do you remember from petrophysics? What is characteristic of clays that you do not find in sand or silt, for example? They swell. And why do they swell? Why? Yes, you're going into the right direction. So a shale is a rock which is made out of. Now the word shale it's used for many applications, including some rocks which are not really shales, but in general shale, and well, I should say specifically shales, are rocks in which a large proportion of the rock is made out of clays. These clays, they are very small, sometimes in the order of a few nanometer width, and they do not look like grains, but they look more like plates with two dimensions a lot larger than the other. And these surfaces of clay, because they are so small, you get to a point in which the molecular forces, they start to take relevance. And if you were to measure the charge of the surfaces, you will see that many of these clays are negatively charged, which means the surface is negative, the core is positive. This is, like the electrotactic repulsion that you get from when you take a sweater off. This electrostatic charge is the same. So clays are electrically charged. And in order to counterbalance this charge, that's where the water comes into the picture. And water is made of oxygen and hydrogen, right? Where the oxygen is the big molecule and the hydrogen are the small molecules, so that when you put them together, it looks like a Mickey Mouse head. Which is the one negatively charged? The face or the ears? The face. The face is negatively charged on Mickey Mouse. And the hydrogens are positively charged. So these molecules of water, you will expect them to be oriented more closely to the clay particles, but that's not everything what you have in brine. So in brine, you don't just have water, but you also have salts. And let's just do an easy example with sodium chloride. Let's say this is sodium, and let's say this is chlorine. Which one is positively charged in sodium chloride? So you will expect the sodium to be closer to these negatively charged surfaces, and the chlorine somewhere in there, probably closer to the hydrogens too. And the distance between these particles is going to depend on how much ions you have in there. The more ions you have, the sooner you counteract this negatively charged surface. So if you have more ions, you can cancel that charge more easily, and as you do that, this layer or this distance is going to be smaller. If you have less ions, then you're going to need more distance in order to counteract all of these negatively charged surface. So at the end of the day, if you make a plot of the distance between the particles, and here the ionic strength of the brine, you will see that these are inversely correlated, so that the bigger the ionic strength, the lower the interparticle distance, and the lower the ionic strength, the bigger the distance. So when we drill, what is drilling mud made of? Well, we got water, for sure. What else? What? Bentonite, what is bentonite? Bentonite is a clay. What else? Barite. What is barite used for? For density control. And what else? We might have salts, and we might have also some additives here. Okay, the salts is the important part, because when you drill with a relatively fresh water, you're going to be somewhere over here. And the rocks are going to be somewhere over there. So when you drill with a mud that doesn't have the same ionic strength as a rock in situ, you're going to cause a change. And in general, that change is going to be that this interparticle distance is going to increase, and as it increases, is going to cause a strain. And that strain, again, is going to cause, if we go to the Wellbore environment, let me finish this. So this is a cross section of the well. And wait, I'm not very happy with that circle. What is the other phase of strains? Because here I'm telling you that if we go from salty water to fresh water, there's going to be a swelling. But we have been saying for a long time that the rock in situ, sometimes it doesn't have the chance to swell freely. So if the rock cannot swell, instead it's going to generate a stress. And for example, if you had your maximum principal stress, or the stress in the plane of the wellbore, the maximum will be in this direction, you will expect breakouts in this location. But if in addition to what you already have, now you have fresh water, which is filtrating into the shale, is going to cause a swelling of the rock, and that swelling is constrained by the geometry of the wellbore, and instead you may have more breakouts just because the rock is trying to swell, but it cannot swell. So this is going to be a drilling mud with low salinity, and it is filtrating into the shale. I hope that you notice that in this case, this is a process that depends with time, because the mud filtrate is not going to get into the shale immediately, but it's going to take some time. So, for example, even though if you had a rock which is very sensitive to fresh water, if you do that quickly, then it might not have enough time for that to go well deep into the rock, and that might not cause a major problem. All right, so other than doing this, drilling this very quickly, what could be other potential solutions for dealing with these shales with instability? I'm gonna give you a hint. Why do we have infiltration in this case? I'm assuming that PW in here is larger than PP. This is what is called overbalanced drilling. So if you don't want infiltration, then what should you do in order to avoid? Let's say you don't have any chance to change your drilling mud. You cannot add salts because you have spent all your money for drilling. And what else could you do? You could do underbalanced drilling, right? Which is that the pressure in the wellbore is lower than the pore pressure. As long as you don't get into any compromise of big breakouts, as long as you don't hit any formation that may have a high pore pressure and you have a kick or something like that, if you know that you're drilling through a long section of shale and underbalance is okay, just go with underbalance. Okay. What else? What else could you do in order to solve this problem? And as you think, I'm going to look for an image that is going to help see what's going on here. Any other solution? What about the composition of the drilling mud? What can we change? We could change the salinity, right? We could bump the salinity up, and in that way we will get a more salient mud. And usually a salt which is very effective for that is a salt called potassium. It's a very strong salt. It's particularly good with smectite. And it's the only downside is that you may have a little more corrosion, and also it's the cost of adding the salt. So it is a solution, but there is one more. What is the problem in here? What do the drilling mud and the rock have in common? The pore fluid of the rock. I'm going to give you, starts with W. This is water-based drilling mud, right? So if you don't want to mess up with the water of the shale, you could use an oil-based drilling mud. And the oil-based drilling mud is not going to hydrate the shale, and therefore it's not going to cause any change of the chemistry in the pore fluid of the rock. So let me move this down here. Just wrote oil-based mud. All right. So I wanted to show you a picture of that, and let's see if I find it quickly. All right. This is an example of what happens to a shale when it is in dry condition or when it is with a high salinity brine, and when you expose it to fresh water. it is not only that it swells, but at some point it loses some of its strength. So it's actually a very complex problem. It's not only the swelling, but also the rock may become weaker as it hydrates. And you can see in the picture right away what's going on. So if in addition to the swelling stress, you have a decrease on the strength of the rock, probably also you'll get even a bigger breakout. In around the wellbore. So that's something to pay attention very closely. All right, let's see. We have 20 minutes. We have 3 more. Okay, the next one is easy. Okay, so we just finished with shear instability. Then number 3. Number 3 is loss of mud support. In all our equations, we have used something very important and an assumption which is key in our equations, and this is that the radial support on the wellbore is equal to the pressure in the wellbore minus the pore pressure in the rock. So this is a radial support, and it is only possible when you have a good filter cake or a good mud cake. What is this mud cake? We talked about a little bit about this. Let's just remind what that is. If you have a rock, and that's why you put bentonite in the drilling mud, because what you want to do is if you have your pressure in your wellbore and your pore pressure over here, what you want to do is create a layer with a low permeability so that this change of pressure going from the wellbore into the rock is very sharp. So this is the pressure of the wellbore, and this is the pore pressure in the rock. This is going to be, the pressure is going to do something like this, and the distance from here to here is PW minus PP. And this acts as sort of a membrane. There's no membrane, but it acts like that. Okay. Sometimes, if you let this mud cake to filtrate over time, or if your mud cake is not very well designed and your particles get into the rock, you might lose that support. What that means is that these particles eventually they're going to get distributed into the pore space, and that barrier is not going to be that well defined anymore. And when that's the case, your pressure is not going to have such a sharp interface as we had before, but it's going to be a lot more diffuse, and it might go to something like this. And when you have that, your sigma RR is not going to be any more PW minus PP. And if that's not the case anymore, then you're not going to have any effective stress on the wall of the wellbore. This is the reason why you cannot drill, or you cannot, when you go to the beach and you make a hole in the sand, you get to the water, you cannot make that hole any deeper. Why? Because you get to the water and you have no effective stress on the wall of the hole. And in these cases, when you do not have any radial support, any mud cake, also you're not going to have this effect. And if you don't have this radial support, your breakouts are going to be a lot larger if you have a cemented rock. If you have an uncemented rock, it's just going to be impossible to make a wellbore in this case. And what is important from here is that sometimes you can design very well your mud cake, but over time you can lose it too. And if you lose it, then again a wellbore that was stable after some time may become unstable. That's why some of those wellbores, if they are not stable open hole, you have to case them as soon as possible so that they do not fail later on. Okay. And what was the fifth one? Okay, the fifth one is short. Okay, let's go to the fourth one. This is a good one. And it is strength anisotropy. If you remember, we said that it was not the same to have a rock which is loaded perpendicular to bedding. That would be a rock which is called perpendicular to bedding in the direction of bedding or at an angle. All right, let's call this one B, this one 45, this one H, horizontal sample. For most rocks, not all of them, but most rocks, you will see that rocks tend to be, the horizontal ones tend to be the stiffer, but not the strongest. The vertical will tend to be the ones that are a little bit softer, but stronger, and horizontal ones will be somewhere in between these two, but will tend to be weaker than the other two. Why are these rocks at an angle weaker than the other two? The 45 already have those bedding planes at an angle. And because of this, when you load them in this direction, if those are weak interfaces, those are going to be the planes in which the rock is going to fail first. If you remember, and this is very important for the midterm on Friday, the optimal angle for shear failure is 45 degrees plus a friction angle divided by 2. So anything close to 45 degrees is going to have on that plane a lot more shear and normal stress than all the other planes. For the vertical, this is like that, and you have a lot of normal stress perpendicular to those weak interfaces. For the horizontal one, also the stresses are not at an optimal angle with respect to those weak interfaces. All right, so let's see what happens when we take this into a deviated wellbore. Okay, so for this rock now, we would like to know what happens when you get a wellbore that does something like this. And where there are sections next to the wellbore, on the wall of the wellbore, in which clearly the actions around the wall of the wellbore are not going to be aligned with the interfaces of the rock. And let's imagine a wellbore that goes horizontal into a rock with a bedding at some deep, something like this. Let me try to get it right. Okay, so I have some bedding here in the rock, and let's say that I have the maximum stress in this direction, the minimum in there. According to the Kear's equation, where should I have breakouts? Let's say this is a vertical. No, well, this could be a, yeah, this could, no, this should be a horizontal wellbore on a with some bedding. So the breakout should be on the sides, right? So somewhere over here, I should have breakouts. But look, let me make a zoom there. Hopefully you notice that in this case, the breakouts, they land on a region in which the rock, it is still the intact rock. It is not the interface. Okay? All right. So now, if I go and consider the anisotropy of the rock, and I look at, for example, which part do you think is going to be more likely to fail? This part of the rock, where I have the interface in this direction, or this one, where it is at an angle? This number 1 or number 2? So let me make a zoom on number 1. Number 1, it is something like this, and it has the interface like that. And number 2, it is something like this, and it has the interface like that. So which one do you think is going to be closer to failure? Number 1 or number 2? Number 2, right? Because the hoop stress and the interfaces are optimally aligned so that it's easier to break the rock in this direction. And because of that, the breakout, it might extend in this direction, but it's also going to grow down in this direction. And on the other side, it's going to be the same. It's going to do something like this. So in this particular case of anisotropic rock, you might have breakouts that are not exactly, or do not appear to be exactly oriented in the direction of the stresses. And that's because of the anisotropy of the rock. And let me show you a very cool example about this. this is what you see over here. Let me get the focus to work. Where this is a shale sample, and you can see the lamination hopefully in this direction, and you see that when it is loaded in this direction, breakouts start here, but they continue growing in this direction and in that direction. And hopefully you can see very well. You can see the fractures over here and over there, and how they continue in this direction. And probably a more dramatic case of that is that one, where the breakout preferentially works, grows in this direction, and here also grows in this one. And I don't know if you can see, but there is also a big fracture going in this case. But it hasn't, the rock hasn't broken yet for this one to fall into the rock. So strength anisotropy is also going to be very important for some of these wellbores, especially when you're drilling into formations which are strongly anisotropic, such as shales. Mr. Cosby, you have a question?
Shouldn't the small areas be SH max?
Here?
Yeah.
It could be SH max or it could be SH min. I'm not meaning that this is a wellbore to do hydraulic fractures. But if I meant this to be a horizontal wellbore, to be perpendicular to minimum principal stress because of multi-stage hydraulic fracturing, you're right, this should be SH max. And consider that this will be also normal faulting. All right, so we have 2 more minutes, and there is one more thing that is important for drilling stability. And now something very important in the Permian Basin, where most of you are going to work. Well, I don't know if most of you, but many of you. And this is an anomalous fracture gradient. If you remember, fracture gradient was the maximum stress or the maximum pressure at which you can pressurize the wellbore. And we're talking in terms of drilling. And that depended on the breakdown pressure PV, but also on the minimum principal stress S3. And let's simplify this in cases where we have normal faulting and strike slip. Then S3 is going to be equal to SH min, and this is going to be equal to sigma H min plus the pore pressure. All right, from these two, which one can we change when we do petroleum-related operations? PP. You can lower PP when you do depletion, and you can increase PP when you do injection. And when you go to areas which are depleted, this is going to result in a low frac gradient, and it's going to be anomalous because that reservoir has been depleted. And when there is a lot of injection, like for example now injection of wastewater or flowback water, you have a very high frac gradient. And if you're not expecting that for natural conditions, then as soon as you hit that anomaly, then that's going to cause some problems. And I think we are on time, guys, so I'm just going to finish here. But I encourage you to read a part that I have over here that I'll find it. I'll find that. But I have somewhere over here examples of low fracture grading. All right? All right. Okay. I'll see you on Wednesday.